Alright guys, today we'll be discussing the concept of an expected value of a random variable. We won't go into detail today about the concept of what random variables are or how they're used. It's assumed you're already familiar with that concept from other probability courses you've taken at UC or another university. So what is an expected value? An expected value is often used to determine the expected results of an experiment that can be repeated. So it might be flipping a coin, rolling some dice, modeling actuarial problems or sales problems. As long as it's repeatable and there's some uncertainty, we can use an expected value. It's often used to just estimate what we think we will get or the outcome of a particular experiment will be. So it's not a guaranteed result. It's merely what we would expect given the uncertainty and the probabilities that we do know. So an expected value is often denoted as EX, and it's equal to the population mean. By now you should be pretty well versed as to what population means are versus sample means, but we'll just do a quick visual representation using areas. So in this larger area we have mu, the population mean, and in this smaller area we'll have our sample mean X bar. And the most common example is testing students, and mu is the population mean, so it's the mean of all students in the world who take the test. And X bar is the average of UC students who take the test. So it's not feasible for us to obtain mu under those kind of circumstances, but the expected value is equal to the population mean. Let's now take a look at the expected value for discrete and continuous distributions. The expected value of a discrete random variable x is equal to the summation of the probabilities of the events multiplied by the events themselves. So we can also express that as a linear combination, but we won't do that in this because it's just not necessary. So from I equals 1 to n can be any number. It can be 5, 10, 100. That's not really relevant. For a continuous random variable, e to the x is a little more complicated than that. The expected value is defined as the integral along the entire domain of our PDF, which we'll get into in a second, of x times the PDF. So this negative infinity and infinity are just notations that we use to denote the domain for our PDF that will be given. Expected values often have a number of unique properties that we can always use and that we should use in obtaining solutions for actuarial problems. And we'll do a couple actuarial problems here at the end of this video. Let's say we want to find the expected value of a function of a random variable gx. How would we do that? Once again, we just take this integral, assuming it's continuous, and our solution is just the exact same. We'll use the PDF to find our solution. It's also worth noting that if we want to find this will be called a higher order moment, but we'll go over that later in another video. There are other ways to obtain these expected values other than integration. We can use a moment generating function, but that's for another time. Is simply x to the n times our PDF, fx. So we also have 3 other important properties that we need to know. So let's assume that we have a constant c, and we want to find the expected value of a constant. What's that going to be? It's simply the constant itself. So we'll get into the other 2 properties here in a second. We just want to clear up some space here before we start attempting to do any problems or anything like that. But expected values are definitely a big part of actuarial sciences and the problems on the P exam. I've taken the exam already, and I can guarantee that expected values, especially multivariate expected values, will most likely be on there. So all of these properties can be extended to more than one variable. Now let's assume that we want to find the expected value of a constant times a random variable. Then we're simply able to take the constant times the expected value of the random variable. This also extends to functions of random variables. So we'll demonstrate that here right now. C is a constant as usual, and we can just summarize these findings like this. Probably the most important thing to remember about expected values, other than of course how to derive them and figure out what they are, is related to variance. So if we have, or we need to find the variance of the random variable x, we need to know that expected values do play a part in that. This is squared if you can't tell. And this is our equation for variance. Alright guys, now we're going to transition into using expected values to solve problems that are going to appear on the actuarial exam using PDFs. So a good knowledge of probability density functions and use substitution is definitely going to help with these type of problems. So this is problem 23.11 in a probability course for actuaries. It says an insurance company's monthly claims are modeled by a continuous positive random variable x whose probability density function is proportional to the following. Where x is between 0 and infinity. So we're just going to denote greater than 0. It's important to note this C is not in the problem. It says it's proportional. That's the key word. C merely denotes a constant that will make properties regarding PDFs true. So what property are we trying to make true? We know that the integral of a PDF across the entire domain has to be equal to 1. So if we integrate this, it needs to be equal to 1. So this is a fairly simple integral, something we would deal with in Calc 2. It doesn't pose much of a problem for us. We get this. And of course we evaluate this between infinity and 0. Once again, not too difficult. We obtain this, and this simply makes us come to the conclusion that C is equal to 3. Now if we didn't have this C, our integral would be 1/3. We would know multiply it by 3 to get 1. So you don't technically need to put this C here if you're familiar with the concept of PDFs having an integral equal to 1 when you integrate over the entire domain of the random variable. So now that we've calculated what C is, how do we find our expected value? So we're just going to use the definition that we went over in the video. We integrate across the entire domain. Of course, this 3 from here. Now we take x times the PDF. And dx, of course. So this looks a little complicated. How can we solve it? All we have to do is a use sub. Usually they cover this in Calc 2. If you're a little rusty, you very well might be. It's worth looking into. So du is equal to dx. So this is how we do a basic u sub. You should be pretty familiar with it. Don't forget to change the upper and lower limits. That's something that students typically forget. It's really important not to. It'll throw off your entire integral, and you'll just have a big mess otherwise. So we substitute in. We're going to transfer this into the denominator and du. Now it just becomes a pretty simple integral for us. We're not too worried about it. We get 3 over u to the 3 minus 3 over u to the 4. Don't forget that du. A lot of professors are insistent upon that. So now that we integrate this, we're going to obtain the following term. Three over 3, u to the 3. These 3's cancel. And of course we integrate from 1 to infinity. And this is going to give us 0 minus negative 3 halves plus 1. So this goes to 1/2. So our expected monthly claim is equal to 1/2. The big key here is the word proportional, especially with regard to a PDF. We now know we need to do this. On a side note, guys, you're probably seeing a little banner up there that says unregistered front cam. That's just the screen capture software I'm using. Don't let it distract you too much. If you guys are interested, I'll be putting up a video about how to actually make videos like this if you want to continue my capstone project, make it more accessible to other students. That'll be another video coming up. Otherwise, have a nice day. Our next video is going to be on moment generating functions, and we'll see you guys then.